All right, great. Welcome everybody to this educators webinar as part of our Polar Professional Development course in Applied Physical Science Concepts for Educators. It's great to have you all join us this morning here in Alaska, afternoon probably where you are. We have Dr. Samantha Hansen on the line, and she's going to be talking to us about seismic investigations of the Transantarctic Mountains in Antarctica. It's the 16th of April, 2013, and I'm going to breeze through some of these slides to get us focused on how to use the Blackboard Collaborate platform. So you should have a slide now that shows kind of a picture of your own screen. On the left, there's going to be video of Dr. Hansen. We don't have video open for everyone, just her. And the participant list shows you who's logged in. And down below that is the chat box, and you're welcome to type in questions or comments throughout the presentation. Sam will try and answer some of those, or we might save them to the end. Also, there's a feature where you can raise your hand to ask a question or share emoticons, whatever you'd like to interact with the webinar. If you do have questions during the presentation, you can type them into the chat box. And at the end, there's that button, looks like a little hand. You can raise your hand, we'll call on you. And the way to use your microphone is to click the talk button that's right above the participant panel on the left. Ask your question, and when you're done, unclick it. And then Sam will be able to answer your question. It'd be great if you can, what we'll do is actually have you type into the chat box so we can get started right away of where you are, if you're part of a school, and any of the number of people that are participating with you. That's great. I know we do have some students on the line that are ready to be listening in, so that's great as well. And just real quick, I want to mention how it is that we are able to bring these webinars to you. It is part of the Polar Trek program, which is a professional development experience for teachers. The main part of our program is a field experience for these teachers in the Arctic and Antarctic. But along with that is additional professional development opportunities, such as the courses we run that Dr. Hansen is a part of at this time around. So with that, I'm going to turn it over to Sam to start with an overview. And Sam, I'll let you take it from here.
Oh, okay. Can you all hear me? Is this coming through? I'm checking the chat box to make sure I get a response. Good. All right. So as Sarah said, my name is Samantha Hansen. I'm coming to you live and in person from the University of Alabama. I will try to keep an eye on the chat box for questions, but it's kind of hard to do that and the slides at the same time. So feel free to save your questions till the end or interrupt me if you need to. If you want to look at the video, that's fine. Hello. But most of you are going to see me staring at my computer and talking to myself, so just bear with me. All right, so a little bit of an overview for the talk today. I wasn't quite sure what everybody's backgrounds were, so I kind of want to make sure we're all sort of starting on the same page. So I'll start with a little bit of background on kind of general plate tectonics concepts and a little more specifically about mountain building. Then I'll talk about Antarctica in a little more detail and the Transantarctic Mountains, which are the primary study location for some of the work that I'm doing. And we'll talk a bit why the Transantarctic Mountains are different than other mountain ranges around the world. Then I'll get into some details on some of the seismic deployments that are going on in Antarctica, including my project, how those deployments are done, some photos from the field, and then we'll get in a couple of analysis examples so you know what's being done with this data. And then at the end I'll wrap it up with a few conclusions, and I'll take any questions or comments you guys might have. So just to begin, again, so we're kind of all starting on the same page, I thought I would do a little bit of an overview of plate tectonics. Basically, the outermost shell of our planet, which is made up of the crust and the uppermost part of the mantle, is called the lithosphere. And the lithosphere is broken up into rigid pieces, which are known as plates, tectonic plates. So the image on the right here is a map, at least part of the world, that highlights some of the different tectonic plates making up the surface of our globe. They're labeled here as well. You'll notice that some of these plates are primarily composed of oceanic material, some are primarily composed of continental material, some are kind of a mix of both. Kind of a big distinction, though, is that oceanic plates are heavier or denser than the continental ones, and so they have the possibility to sink back into the mantle in a process called subduction, where the lighter or less dense continental plates don't do that. They can't subduct and dive back into the mantle and into the Earth. Most of the real action going on the planet takes place at plate boundaries, so where two or more plates are coming together in some kind of fashion. And so the little insets down here labeled A, B, and C illustrate three different types of plate boundaries. The first one here is called a divergent plate boundary, where two plates are diverging or moving away from one another. Thank you for the little hand. I'm going to jump over to C real quick. That's called a transform boundary, where basically two plates are moving past one another side by side, so just horizontal motion, no vertical motion. And then coming back to the one in the middle, letter B here, that's called a convergent plate boundary, where two plates are converging or coming together. And again, depending on what kinds of plates you're dealing with, again, oceanic versus continental, you can get some different things happening at each of these different kinds of plate boundaries. Oops. There we go. So what we're going to focus on a little more today is the concept of mountain building. And as shown in the cartoon here at the top, generally speaking, most mountains are created or built through, again, convergence or collision between two continental plates. So we've got two continental plates here running into one another, kind of a head-on car crash between the two. And basically, the material in the middle of that collision is getting shortened and thickened, basically pushing material up into the air. Because again, continental plates are less dense, they're very light, they can't subduct down into the earth, and so you're pushing that material up into the air, forming a mountain. And so again, this is sort of the traditional way or standard way which most mountain ranges around the world have formed. And just for reference, I've put two pictures down on the bottom here of two examples of mountains that I think most people are familiar with that formed in this manner, that being the Himalayas, which are formed and currently forming today, which is a collision between the subcontinent of India colliding or converging with Eurasia. And the other picture here is the Appalachian Mountains, a considerably older mountain range that was formed again through continent-continent collision of past events. So kind of keeping that all in mind, we're going to transition our discussion a little bit here to Antarctica. I like this slide because it kind of hits a lot of the what I call fun facts about Antarctica. I think most people find these kind of interesting. So the map here on the right is just to help get you oriented if you're not familiar with this part of the world. Obviously the blue continent here in the middle is Antarctica, and this is basically what the world looks like if you were looking at it from bottom up, so kind of tilted on its side. And just to put it in relation to some of the other continents, right here is the tip of South America sticking down here. We've got the tip of Africa up on the upper right, and then kind of down on the lower right we have Australia and New Zealand. So again, just to kind of get you oriented. Antarctica is actually the 5th largest landmass on this planet, so it's a pretty good chunk of real estate. It's about 1.5 times the size of the continental United States. It's been described as the coldest, windiest, driest, highest, quietest, most remote, and least understood continent on planet Earth. It definitely fits the bill on all accounts. It is actually the world's largest desert, something a lot of people don't realize. There are parts of Antarctica, like the dry valleys outside of McMurdo, if you happen to be familiar with those, that have not received any precipitation in millions of years. So really quite arid place. And probably not too surprising, it's pretty cold there. Actually, the world's coldest temperature on record was recorded in Antarctica, near a Russian base called Vostok, at a brisk negative 129 degrees below zero. And it's 99.6% covered by snow and ice. So this can make surface observations a little bit difficult because you can't really see the rocks and the geology that you're looking at. And so we're going to talk about some different ways that we can investigate Antarctica since we can't just go out and look at it directly. Is everything going okay, Sarah? I see a lot of these comments about choppy video and stuff.
Yeah.
Okay.
Actually, Sam, I was going to have you call into our number.
Oh, okay. Can you remind me what that is again?
Yeah, we'll put it in the chat box for you. She needs the participant code as well. Oh, she could be on the phone with you to talk. All right, Sam, and mute your computer.
Okay.
The talk button one more time. Yep, can you press the talk button one more time?
Okay.
And unclick.
I'm getting like a weird feedback.
Yep, Sam, that's because your audio is still on your computer, but that's a great way for us to get your video again. So I'm gonna play with the video for a second, but go ahead and continue with the presentation through the phone.
Okay, I just muted the computer, so I can't hear you through that now.
Can you hear me through the phone?
Yeah, I can hear you through the phone.
All right, perfect. So everyone can hear you, and you should be able to continue, and I'll work on your video.
Okay. Should I just pick up where I left off, or?
Yeah, I think that would be okay.
Okay. All right. If anybody has questions, feel free to jump in. All right, so we finished this slide, and like I said, basically Antarctica is almost completely covered by snow and ice, so it makes it very difficult to make direct surface observations there. So kind of getting more into the study area that I'm focusing on, we're going to talk about the Transantarctic Mountains, which I tend to refer to as the TAMs. So if you hear me say that, that's what I'm talking about. As you can see from the map over here on the right, the TAMs are a very long mountain range, about 4,000 kilometers long, and have elevations up to about 4,500 meters. And they run roughly through the center of the continent, roughly splitting it in half. Separating Antarctica into what's called East Antarctica and West Antarctica. I've also marked South Pole, roughly the location of South Pole on this map. Directions get a little weird when you're at the bottom of the world because literally every direction is north.
And Sam, can you just speak up a little bit?
Oh, sure.
All right. Folks, let us know if that's better while she's talking.
Okay, sorry. We good? Okay. So, like I said, South Pole is also marked on the map here. Directions are a little strange when you get to Antarctica because everything is north. So this is sort of the convention when referring to directions. So basically everything on the left side of the Transantarctic Mountains is considered West Antarctica. And it's thought that West Antarctica might be undergoing continental rifting, basically pulling this area apart. Everything on the right side of the Transantarctic Mountains is considered to be East Antarctica, which is thought to be basically old, stable continental material that's been coherent for a long time. The TAMs themselves began uplifting about 55 million years ago, and there's various geology observations and other geochemical observations to support that. But what makes the Transantarctic Mountains kind of strange is there's no evidence for a compressional origin. So again, that model that we looked at for running two continental plates together and compressing the area in between doesn't seem to apply to this particular mountain range. Just to kind of drive the point home here, this is just another image of Antarctica. This is what's called Bedmap. So what you're looking at here is basically the surface topography of the continent if you took all the ice sheets away. And so again, we've got some red arrows here pointing out some features. We've got, again, the Transantarctic Mountains, or the TAMs, kind of running up through the middle of the continent, basically splitting West Antarctica from East Antarctica. And again, you can see that West and East Antarctica look fairly different from one another. East Antarctica is fairly high, very high plateau region, where West Antarctica is much lower. Some parts of this are at or even below sea level. So the TAMs separate two very different parts of the continent. So some important questions related to the Transantarctic Mountains. First, how did they form? By what process did they form? Again, the TAMs don't display any evidence for sort of this traditional compressional origin between colliding two continental plates. And so if that's the case, well, how did they get there? How did they form? Kind of related question, how does the formation of the TAMs relate to the overall tectonic history of Antarctica? So again, what role did the formation of this mountain range play in sort of the bigger scale image of how Antarctica as a continent came together? And thirdly, what role did the TAMs play in the glaciation of the continent? It's been suggested by a lot of climate glaciology models that basically the large-scale glaciation of Antarctica started at the higher elevation points, such as the TAMs, and it spread out from those locations. So again, when exactly did that happen, and how did that evolve?
All right, Sam, I'm just going to ask you real quick, just press the talk button and then press it again. We'll see if your face shows up big.
Okay. Did that work?
Okay. No, keep talking. That's all right.
Okay. There's nothing much to look at anyway, except me with my phone pressed against my head staring at my computer. So.
Don't worry. Thanks.
Okay. So on this slide here, I've just shown a couple of the different models that have been suggested to explain the uplift or the formation of the Transantarctic Mountains. And again, this is not all-inclusive. There's other ideas that have been put forth as well. But again, since the TAMs don't have this compressional origin, how else might they have formed? So the top picture here is from a study that was done back in 1989 by Stern and Tenbrink. And their idea was basically what's illustrated here in what they'd call a flexural and thermal loading model. So basically on the left side of the image, we have East Antarctica butting up against West Antarctica on the right side of the image. If you remember, I told you just a minute ago that, again, East Antarctica is thought to be kind of old, stable continental material, where underneath West Antarctica it's thought that you have rifting, continental rifting going on, again, pulling the area apart. If that's the case, then the mantle beneath West Antarctica should be hot, buoyant, and come up a little bit higher. And so basically the buoyancy of that hot material, because hot things like to rise, basically push on this broken edge of the East Antarctic plate, kind of help push it up in the air, ultimately uplifting the Transantarctic Mountains, which lie right on the boundary between these two. Additionally, you have some erosion that might have gone on here that also, again, for balance and isostasy forces, help lift the Transantarctics up in the air. So that's their idea of how this TAMs maybe came into being. The other image on the lower right here is from a different paper that came out in 2004 by Studinger et al. This was a model based on area geophysical data. So the top panel here is basically just a profile across their study area. Again, they've got the Transantarctic Mountains here over on the right. The sort of light gray area indicates where it's covered in ice, and then the dark gray area below that is the, again, bedrock topography. If you look down at the lower panel here, they have this dashed line, and basically that's their modeled estimate of how thick the crust is beneath this part of their profile. So you'll notice I've pointed it out here with this blue arrow, that in their model they have a low density route, a crustal route beneath the Transantarctic Mountains that basically, again, help to provide sort of an uplift or a buoyancy force to help push these mountains up in the air. So again, these are just two example uplift models that have been suggested to explain how the TAMs came into being.
Hey, Sam, we do have a question.
Oh, sure.
Yeah, so Olivia from Lolly Garay's class is asking, do we know how long it took to form TAMs?
I mentioned this on a previous slide, but I know there's a lot of going back and forth. It's been estimated that they started uplifting about 55 million years ago. How long it ultimately got them to reach their current position, I'm not exactly sure, and I don't think we really know that.
Thanks.
Yep. So, to try to get at the details of exactly what's going on beneath the Transantarctic Mountains, how they might have come into play, which of these models might potentially be correct, we really need some details about, how thick is the crust beneath this region, what's the upper mantle structure beneath the TAMs, and other details like that, which could basically help us determine which suggested model or models might be the most viable. So, do you have a low-density crustal route beneath the mountains, such as in the Studinger example, or do you have this hot buoyant mantle pushing up beneath the area like the Stern and Tenbrink model? So to start getting at some of this data, again, looking at crustal and upper mantle structure, I employ data from various seismic networks that have been deployed around Antarctica. And so in this slide, the bigger map on the upper left here basically shows all of the, at least larger scale seismic deployments that have been done in Antarctica. Some of these are still operating now, some of them aren't anymore. I basically put the names for each one of these experiments on the map as well. There's also this red box down here that shows a little inset that I've blown up on the lower right. And you'll notice the little purple markers in that box. That's the TAMNet array, the Transantarctic Mountains Northern Network. And that's actually the new seismic array that we just put in this past season, along with Brian's help. So we're still waiting on data to come in from those. We'll be going down later this year to get our first batch of data. And data from those stations, as well as data from a lot of these other stations that you see on here. All of these stations basically record long-range earthquakes that happen all around the world. And we can use the signals from those earthquakes to kind of see into the substructure. And I'll elaborate on that a little more later. So just to give you an idea of what we're doing out there, I thought I'd share with you some pictures from our field work. So the two pictures here on the left, these big orange boxes, basically show the guts of our station, if you will. The boxes basically contain batteries and all of the electronics associated with our equipment, so data recorders and that sort of thing. The stations also have a connection to a solar panel that I'll show you a little bit later too. So they run on solar energy during the summer in Antarctica when it's light all the time, but obviously it's dark all the time in the winter, so then they have to run on battery power. And each one of these boxes gets deployed to a different station. They each weigh about 600 pounds, so they're kind of fun to move. Those boxes and then some other equipment that I'll show you in just a minute get loaded onto one of a couple of different transportation options. Most of the time we're using Twin Otter aircraft, so these little prop job airplanes that are shown on the upper right picture here. And this last season though with the TAMNet deployment, we were lucky enough to install some of them using A-Star helicopters. So this is me standing in front of one of the helicopters we had. We actually had two of those. The people generally rode out in one helicopter and all the equipment in the other, including a sling load that hangs below the helicopter to get it to where it's going.
Hey Sam, we have a quick question from Josh in Lolly's classroom. How do batteries keep from freezing?
It's a good question. As you can probably see, at least in the top left picture here, that kind of blue styrofoam you can see is all insulation. So the boxes are insulated pretty well. The electronics themselves do produce some heat inside that box, and there is a little heating pad in there as well that helps keep the inside of the box warmer. That being said, we are using special batteries for a lot of our stations. There are some kind of quote-unquote regular absorption glass mat or AGM batteries in there if you're familiar with those. But we're using lithium batteries, and there's, depending on the type of station, there's up to 10 lithium batteries in a box, and each one costs about $10,000. So just my battery budget for this project was $180,000 to do 15 stations. So.
Wow, thank you very much, Sam.
Yeah. Okay. So getting on either the Twin Otter or the helicopter, we then fly out to wherever we want to deploy the station of interest, and we get to dig a lot of holes in the snow. So this is me digging. We dig a lot of holes. We basically at every site dig 3 holes. There's one big hole dug for that big orange box. There's another hole that I'll show you in a minute that the actual seismometer, the instrument that records the earthquakes, goes into. And then we have a somewhat smaller hole for the solar panel. So if we jump down to the lower right image here, obviously there's a hole that's dug in the snow here, and they're lowering that big 600-pound box into that hole. If you look over this guy's shoulder, this is our pilot Travis, this thing that kind of looks like a lampshade behind him with a spool of cable on it, that's the solar panel. Oh no, go to the left. There you go. That's the solar panel that provides power at least during the summer months.
And how many, this is Sarah, Olivia is asking, how many does it take to run the array? I think she means batteries.
Oh, how many batteries is it? Again, it depends on, we have actually 2 different setups of stations. Ones that are kind of up on the East Antarctic Plateau are operating at somewhat colder conditions, and so they have a little different battery configuration, but ballpark estimate about 10.
All right, thanks.
Okay. So let's see. So then, let's see, here's me standing in another big hole. That little green dome thing in the hole is the actual seismometer. It's a polar rated seismometer, so they have been tested to operate in these kind of conditions. And that's the instrument that actually detects and records the earthquakes from around the world. Also, I kind of pointed this out in the last slide in the lower left picture here. Again, that's the solar panel. This guy is Doug. He's one of our technicians, and he's helping hook up the solar panel. And if you go over to the far right here, this kind of shows a nice representation of the full setup. So in the foreground here, that little blue and white hat is sitting over the seismometer, basically to help keep it insulated. You can kind of follow the cables back into the picture. Again, you can see the orange box that's open here. We're putting equipment and such into it. And then a couple of solar panels in the background there closer to the helicopter. So once everything is hooked up, tested, we know it's working, we throw a big orange dome over the seismometer. Yep. And again, this helps to insulate the system and help keep things nice and quiet, kind of protect everything from the wind. And we backfill it in with snow, basically bury everything more or less completely over. And we put these big bamboo poles around, sticking up into the air. So basically, this thing is going to sit here for the next year and record earthquakes from around the world. The poles are basically just markers, so when we come back a year from now, hopefully we can find this thing and dig it back up and get some data out. And then I just put this other picture in here to be funny. This was when we had completed our final of our 15 stations. We were very happy that we got everything done. So this is me here in the middle, and Brian is standing right under where it says Ken, of Ken Borg Air. Oh, that's my grad student. There you go. There's Brian. So what are we going to do with all this? The seismic data that we're recording, and again, the data that's available from other stations in Antarctica, get processed in a variety of ways. So again, we can basically see, quote unquote, into the subsurface beneath the Transantarctic Mountains or wherever else we're looking at. And so I've kind of illustrated these with the two pictures here. The lower left image just illustrates some of the different paths that energy from an earthquake, the earthquake shown with the little red star here, energy from an earthquake travels out in every direction through the Earth, and it can take different paths through the Earth. So sometimes it may go down and bounce off the surface of the Earth, like in the red line here. You can have phases or paths of energy that goes deeper into the mantle, maybe all the way down through in different parts of the core. And so there's all different paths and all different phases of earthquake data that we can use. The image on the right here is meant to represent, so if you have an earthquake far away and it sends energy through the Earth, at least some of that energy is going to come up through the subsurface of your study area, so basically coming up through the Transantarctic Mountains here, up through the snow and ice, and ultimately getting recorded at our stations on the surface. And so as it says in the text here, we can basically model the timing, the amplitude, and other characteristics of this seismic signal, these earthquake signals, to look at structure beneath the ground in our study area. So I just thought I'd show you a couple of examples of how you might go about doing this, and I'm going to keep this pretty simple. This is one example of a seismic analysis approach. It's called a receiver function. As shown on the left here, when you have seismic energy moving through the subsurface, and that energy hits some kind of boundary or a discontinuity, part of that energy is going to change or convert from one type of wave to another. So you may notice here we have two types of waves shown here by the blue and the red lines, P waves and S waves, which are two different types of seismic waves. And you'll notice that at least on some of these paths, we're converting one type of wave to another. And so the converted signal may look something like this other box just below here. Basically, again, we can model that converted signal, basically how big those peaks are and the timing of those peaks, to figure out where those boundaries in the subsurface are. So you're kind of back calculating, if you want to look at it that way, trying to use the signal to figure out where boundaries are. For instance, one boundary you might be interested in is the interface between the Earth's crust and the Earth's mantle. The lower picture here is from an earlier study that I did looking at data from a different seismic deployment, which also crossed at least part of the Transantarctic Mountains, a different part than we're looking at now. Basically, the solid black line on top is the surface topography. The blue shaded area is where you have ice coverage. And then the black line down here with the dots and the error bars are basically my estimates of crustal thickness. So again, where is that crust-mantle interface beneath the study area that we've modeled using this approach? And so this
Hi Sam, this is, oops, sorry. This is Judy.
Sorry.
We have a quick question also coming in. How long have you been working on this project? Brianna wants to know.
TAMNet itself, I got it funded about a year ago, and we deployed all of our stations just this past season, so November and December. So they've been out there operating since then. We haven't actually gotten our first batch of data yet from those stations, and so we're going to go down and get them later this year. I have worked on other seismic deployments in Antarctica. So like, for example, this image on the lower right on the screen right now is from a different set of seismic data that I worked on previously.
Thanks, Sam.
Yep. Did I miss part of the question, or did I answer that all?
You got it.
Okay. So like I said, this is just one approach of an analysis method that we can use to look at our seismic data. One other example of what you could maybe do with your seismic data is something called tomography. Tomography you kind of think of it like a CAT scan of the Earth, and that's what this picture on the right here is trying to show. So,
and Sam, if you could speak up again, that'd be awesome.
Okay.
Thanks.
I have to keep adjusting my phone. So the image on the right here, these orange dots are meant to represent earthquakes. And again, those black lines are the different paths that energy is taking through the Earth, so very similar to the picture I showed you before. Ultimately getting recorded at stations that are denoted by these little blue triangles. Basically, we can look at the speed at which these rays pass through the Earth and can basically compare it to reference velocity models of the Earth. So where you can see differences between, again, how fast or slow that ray is actually traveling versus an estimated velocity for it, can give us an image of where you have areas of the subsurface that are a little faster or areas of the subsurface that's a little slower. So this lower picture here is from a paper by Tim Watson that came out in 2006. These was using data from, again, a different Antarctic seismic deployment called TAMSIZE. Mine's called TAMNet. But basically the colors on here that you're looking at represent the velocity at which a particular kind of seismic wave called a P wave moves through the subsurface. So the areas that are colored blue, as you can tell by the scale here, are moving a little bit faster, while the warmer kind of red and yellow colors are moving a little bit slower. And so there's interpretations that can be made, again, looking at this pattern of fast and slow. So just to kind of wrap things up, the Transantarctic Mountains, or the TAMs in Antarctica, are kind of an unusual mountain range because they don't really show sort of your standard compressional origin. They didn't look like they formed through kind of typical continent-continent collision. So to really start deciphering how the TAMs developed and how they originated, we need to get more details on their corresponding structure, primarily crustal and upper mantle structure. And so we're doing that by using seismic data from stations deployed around Antarctica, and basically using these different techniques to model our seismic data and ultimately investigate the subsurface and try to decipher what some of these different models are. So with that, I'll leave you with some fun pictures. A lot of these are from previous Antarctic field seasons as well. I thank you very much for your attention. I'm sorry if there was problems with the audio or video. And if you have any additional comments or questions, I'm happy to take them.
Great. Thanks, Sam. All right. People might have some questions, so we'll let them kind of formulate those. I appreciate all the information in the webinar. It was really helpful. It was great to have you start from the very beginning with mountain building processes and moving forward to exactly what you do. And Lolly's actually saying her students are filing out for the next class, so I'm glad they got to listen in to all of Sam's talk. Thanks for joining us. Julia is saying, it seems like it's almost like sonar to map ocean floors. Sam, do you want to comment on that?
It's not totally dissimilar. I guess the difference, sonar is kind of works on the process that you're sending out a signal and it bounces off something. It reflects back and comes back to you. And there are other, seismology is under sort of a larger branch of science called geophysics. And there are other geophysics methods that kind of take that approach. So they'll send out some kind of signal, bounce it off, say the surface of Antarctica, like the bedrock, for example, and get a signal back. Ours is a little bit different in that our signals are actually going through the entire Earth. So you get an earthquake that occurs somewhere far away, sends that signal through the entire Earth, so it's moving through the Earth that you want to sample, and ultimately we record it and then again do modeling and such with that data to infer structure that we're interested in. So it's somewhat analogous.
Great. Yeah, Julia's saying, yes. Good, Julia. I hope that helps. And so Justin has his hand up. Justin, if you'd like to use the microphone, you can press the talk button and speak, and then press it again when you're done.
I'm wondering if we are aware of any other mountain ranges that were formed in the same manner or a similar manner.
Well, since we don't really know how the TAMs formed yet, it's a little hard to answer that question. But I guess if you're asking if there's other non-compressional mountain ranges around the world, there are. Kind of the immediate example I can think of that I'm familiar with are the Tetons, if you're familiar with those up near Yellowstone. The Tetons are significantly younger than the Transantarctic Mountains in Antarctica, but again, don't show this kind of compressional origin. And I think the prevailing thought there, and I haven't done a lot of work in the Tetons, so kind of forgive me if this isn't completely correct, but again, Yellowstone is nearby. It's a hot spot, and I can talk about what that is if people are interested. But basically, again, you have hot, buoyant material pushing on the area from below, kind of helping to push it up in the air. So it's a mountain range that formed, again, through non-compressional methods. The TAMs, so again, I guess the TAMs aren't unique in that they're the only non-compressional mountain range in the world, but they're the largest non-compressional mountain range in the world.
Great. Thanks, Sam. Lolly's asking, did you pick up the earthquake today?
I'm sure I probably did. I can't tell you yet because I can't access my data real time. We don't have the infrastructure or the broadband signal in Antarctica to send data back to us. So the only way we're going to get that data is to go physically get it, which is the plan for somewhat later this year.
Thanks, Sam. That was good. Now let's see if anybody has last few questions here as we begin to wrap up. For other folks, just so you know, this is part of a larger course that Dr. Hansen is a part of, as well as Brian Dubé, who was on the phone a little while, or on Blackboard a little while ago. He had mentioned he had a fire alarm. There was actually a small fire in the girls' bathroom, so he's still outside trying to figure out what's going on. But I will turn this over to Justin. He's got another question, so press the talk button when you're ready, and again when you're done.
I think you mentioned that the TAMs have played some kind of role in the glaciation on Antarctica, and I was wondering if you could address that a little bit.
Yeah, so as I mentioned, it's been thought, a number of people who do sort of climate studies, glaciology studies, sort of looking at the glacial history of Antarctica, if you will, have suggested that the large-scale ice sheets that cover the continent basically originated at topographically high points. So I'm going to jump to a different slide here real quick. Why is it changing? There we go. So for example, looking at this map here, again, this is what Antarctica looks like with no ice sitting on top of it. And so you can notice basically the areas that are colored sort of yellow and into orangey red are sort of the high points of Antarctica, so including the Transantarctic Mountains that we talked about today. Over in the middle of East Antarctica, there's another high point kind of in the middle of East Antarctica. Yep, that's the Gamburtsev Mountains, and I've done some work on those too. They're completely subglacial, so completely buried in ice, but they're as big as the Alps. But when you're out there, it looks perfectly flat because they're buried up to 2 to 3 miles under the ice. So really quite amazing. And there's a few other high points around that you can see as well. And so the thought is that these high points in Antarctica, these high topography regions, basically were sort of the origins, if you will, of where the ice sheets originated, and then they spread out and sort of connected with one another and ultimately covered basically the entire continent. And so the questions become of, how exactly did that happen? What time frame exactly are we talking about? And a lot of the work that's being done to look at glacial and climate studies actually is fairly closely tied to a lot of the work that I'm doing and other people like me are doing, because there's an importance in knowing characteristics about the subsurface that help you understand how glaciers respond. And so it's almost like looking at a shock absorber, you know what I'm trying to say, system, in that, you know, what are the characteristics of the subsurface and how this thing is going to bend and flex and react to all of this weight of this ice sitting on top of it. So there's a lot of work being done between people who are looking at, for example, ice sheets and how the ice sheets are changing and climate effects and that sort of thing, and people like me who do geophysical work and try to understand the surface and the subsurface and how all of this ties together.
Great, perfect, Sam. And then it looks like Julia has a question. If you're ready, press the talk button and then press it again when you're done asking.
Question about the equipment. You mentioned you don't have the broadband there to get real-time data. I know that in Antarctica there's intermittent satellites, right? They come occasionally. If you did have, well, two questions. One is, most seismograph data in the world, is it collected real-time through satellite and internet, or is that still relatively new? And is there the possibility of you getting intermittent data if you had the equipment? Thanks.
No, that's a really good question. It kind of depends where you're working and what the local infrastructure is. So for example, I also do a lot of work in Africa, and in most places in Africa, we've got enough infrastructure and signal that we can send at least part of the data back real time. Antarctica is just so remote, and there's just not the technology we need there yet to send it back. Now, that's not saying we can't send back any data. Most of the stations have little modems attached to them that send back what are called state of health files on a fairly regular basis, which basically just lets us know that the system is operating as it should. It will send back little snippets of data and things like that. But again, we don't have the capacity to send back as much data as we need to work with. We're recording data. It basically records all the time, and we're recording at different sampling rates. But some of this data is being recorded at 100 samples a second. So you're recording a lot of data. And so to try to send that back, we just don't have the capability. But I mean, eventually they're working on methods to try to improve that, because obviously having to go down every year just to get the data, inevitably you end up doing some kind of maintenance as well while you're there, because it's a harsh climate. But you know, it becomes very expensive and kind of tedious, you know, logistically. And so, you know, they are working on ways to improve that, but it's still just not possible for us to get the data back that we need. So.
Perfect. Thanks.
Yep.
All right. Well, I'll just see for a second here if anybody else begins to type into the chat box or wants to ask a question. But for those that are enrolled in our online professional development class, you can continue asking questions and having this discussion through our group site throughout this week and next week. And I'll also mention now that this webinar will be archived as soon as possible, and I'll be sending out the archive links to everybody who's participating and those who are also registered but couldn't make it to this webinar. They'll be watching it this week, the other participants in our class. So it looks like people have wrapped up with their questions. The last few things that we'll say is that teachers can become a part of Polar Trek in multiple different ways, including the participation in these online professional development courses. There's the email list. There are many, many other Polar Connect events as we begin our Arctic field season this summer, and the expeditions for the 2013-14 field seasons are all up and running, so check out the website. You can look for upcoming events at polartrek.com, and what we would like to do is just make sure we say thanks to Sam for her work and her participation in our course. And we will also be having a webinar next week with Brian Dubé, and he was the teacher that went out with Sam on an expedition this last U.S. winter.
Yeah, well, thanks very much. You're all very welcome. I feel thank yous coming in. And yeah, be sure to check out Brian's presentation too, because he's done some really cool stuff with videos and kind of highlighting a lot of the work that we did when we were in Antarctica. So.
All right. Thanks, everybody. It looks like everybody's saying thanks, and awesome presentation down in the chat box. So we'll end the recording and let you all sign off for the day. Have a great one. Take care.
Thanks a lot.